Invisible bullets from deep space are hitting our planet right now. These are ultra-high-energy cosmic rays, and they carry more power than any machine humanity has ever built. They are one of the greatest unsolved mysteries in all of science. We are about to journey through 50 specific cosmic events that have left the world's smartest physicists completely stumped. By the end, you will know the details of 50 real cosmic puzzles that defy our current understanding of the universe. We will explore where they might come from and why they should not even exist. Are you ready to see how many cosmic secrets are still waiting to be uncovered? It arrived in the sky above Utah on a clear October night in 1991, an event so shocking it earned the name the "Oh my God" particle. This was not just another cosmic ray, it was a single subatomic speck, a proton smaller than an atom, yet it carried the kinetic energy of a professionally thrown baseball. Imagine the force of a 5-ounce sphere smacking into a catcher's mitt at 60 miles per hour. Now compress all that raw, destructive power into a particle a trillion times smaller than a grain of sand. The numbers are almost impossible to grasp. This one particle hit our atmosphere with an energy of 320 exa-electronvolts. It was millions of times more powerful than anything produced in the most advanced particle colliders on Earth. Its detection did not just break a record, it shattered the very ceiling of what physicists thought was possible for a particle traveling through the cosmos. The theoretical limit, known as the UHECR cutoff, had long been a fundamental rule. It stated that particles with such immense energy should be destroyed on their long journeys, constantly bumping into the faint glow of cosmic background radiation until they bled away their power. The "Oh my God" particle ignored this rule completely. It arrived with virtually all its energy intact, a cosmic speedster that should not have been able to survive the trip. This single event forced scientists to confront a terrifying question. What kind of cosmic cannon could possibly accelerate a particle to such an unbelievable velocity? The leading suspicion points far beyond our own Milky Way galaxy to some violent extragalactic source, but that only deepens the mystery. If it came from another galaxy, the journey through intergalactic space should have slowed it to a crawl, stripping its energy away. The fact that it did not slow down means our understanding of physics itself is fundamentally incomplete. We are left staring at the data, forced to reconsider the very laws that govern the universe, all because of one tiny, impossible particle that refused to play by the rules. That single particle was not an isolated fluke. Decades later, a sprawling network of detectors in the Utah desert is actively hunting for more of these cosmic anomalies. This is the telescope array experiment, a silent sentinel composed of over 500 scintillator detectors spread across 300 square miles. It watches the sky for the faint secondary showers of particles created when an ultra-high energy cosmic ray smashes into our atmosphere, and it has found them. The experiment has recorded over 30 events with energies soaring past 100 exa-electronvolts, confirming that the "Oh my God" particle was not a solitary mistake. It had siblings, but this confirmation only twisted the mystery into a new, more baffling shape. When scientists traced the arrival directions of these monstrous rays back to their points of origin, they were met with a profound emptiness. The paths did not lead to brilliant quasars, violent supernova, or colliding galaxies. Instead, they pointed toward vast, dark voids in the fabric of space, regions of the cosmos that are practically empty, containing little more than a few scattered, dim stars. It is like tracing the path of a high-powered rifle bullet back to its source, only to find it came from the middle of a silent, deserted field. This makes the existence of these particles even more perplexing. The theoretical framework that should prevent their arrival is known as the UHECR cutoff, named for the scientists Greisen, Zatsepin, and Kuzmin. This is not just a suggestion. It is a fundamental law of cosmic travel for high-energy particles. The entire universe is filled with a faint, cold afterglow from the Big Bang, the cosmic microwave background radiation. Think of this as a thin, cosmic fog that permeates all of space. According to well-tested physics, a proton traveling across millions of light-years should constantly bump into these fog like photons. Each collision would sap a little of its energy, like a marathon runner constantly tripping over tiny, invisible hurdles. For a particle starting from a distant galaxy, this process should grind it down, ensuring that nothing with an energy above about 60 electron volts could ever reach Earth. The rays detected by the telescope array, some with energies 5 times that limit, are not just bending this rule. They are shattering it. They arrive with a punch that should have been drained away eons ago. So what does this mean? We are left with 2 equally staggering possibilities. Either our understanding of particle physics itself is wrong, and these protons are interacting with the cosmic fog in a way we have not yet discovered, or there are unimaginably powerful engines lurking in those seemingly empty voids, accelerating matter to impossible speeds. What kind of cosmic phenomenon could be so powerful and yet remain so perfectly hidden in the dark? 3 years after the Oh My God particle, another record-shattering event illuminated the Utah sky. In 1993, an experiment with a strangely beautiful name, the Fly's Eye detector, captured a cosmic ray with an energy exceeding 3 times 10 to the power of 20 electron volts. This was not merely a confirmation. It was a declaration that the universe was routinely producing particles with energies that defied all reason. The Fly's Eye itself was a masterpiece of ingenuity designed to see the invisible. It did not look for the particles themselves, but for the faint, ethereal glow they left behind. Its design used a vast array of mirrors, each resembling the compound eye of a fly, to collect the tiny pulses of ultraviolet light produced when a cosmic ray collides with the atmosphere, creating a sprawling cascade of secondary particles. This innovative approach allowed it to see the faint signature of these incredible events with unprecedented clarity. The detection was a triumph for the novel technology, but its implications were profound. With this second monumental detection, the scientific community could no longer dismiss the Oh My God particle as a once-in-a-lifetime fluke or a potential instrument error. These ultra-high-energy events were real, they were recurring, and any credible theory of cosmic rays would now have to account for their terrifying power. Yet, just as with its predecessor, the mystery only deepened when astronomers tried to trace its origin. They looked along its incoming path, searching for a cosmic culprit, a brilliant quasar, a turbulent galaxy merger, or a nearby active galactic nucleus with a monstrous black hole at its heart. They found nothing. The direction from which this colossal particle arrived was a quiet, unremarkable patch of intergalactic space, devoid of any known source capable of such an immense acceleration. This consistent pattern of arrival from the cosmic voids presents a puzzle that is both elegant and infuriating. It suggests that our maps of the universe's most powerful objects are fundamentally incomplete, that we are surrounded by cosmic accelerators of unimaginable force operating in perfect silence and total darkness. What could possibly be hidden in the emptiness, and how many more of these cosmic bullets are still flying toward us, completely unseen? Far to the north, in the vast Siberian wilderness, another cosmic mystery was quietly unfolding. The Yakutsk Array, a sprawling network of detectors buried deep in the permafrost, recorded an event that stood out not just for its raw power, but for what it appeared to be made of. When this cosmic ray struck the atmosphere, it created a sprawling cascade of particles, a grand air shower that was meticulously analyzed by scientists. The telltale signature of that shower suggested something extraordinary. This was not a simple, lightweight proton like the Oh My God particle. The evidence pointed to a much heavier traveler, likely a nucleus of iron, an entire atomic core stripped of its electrons, hurtling through the cosmos. This single detail transforms the mystery into something entirely new. A proton is a tiny, rugged speck capable of surviving a long, tumultuous journey. A heavy nucleus like iron, however, is far more fragile, a clump of protons and neutrons held together that is easily shattered. According to our established physics, such a heavy nucleus trying to travel across intergalactic space would be torn to pieces. It would constantly collide with the photons of the cosmic microwave background, that pervasive cosmic fog, and these interactions would act like a relentless hammer, breaking the iron nucleus into smaller and smaller fragments long before it could ever reach Earth. The mere existence of this iron cosmic ray, intact and carrying immense energy, forces a stunning conclusion. It could not have come from very far away. Its source must be relatively local within our own cosmic neighborhood, perhaps even inside our Milky Way galaxy. This should make the puzzle easier to solve, right? We simply need to find a powerful object nearby that could have launched it. Yet, when astronomers scan the region of space from which it came, they find nothing capable of such a feat. No nearby supernova remnant is powerful enough. No pulsar or stellar explosion in our galactic vicinity fits the bill. We are left with a cosmic contradiction, an object that by its very nature declares it originated nearby, but for which there is no local source to be found. How can a heavy nucleus survive a journey that should destroy it? And where is the hidden particle accelerator in our own backyard that we have somehow failed to see? That faint, flickering signal of a hotspot came from Japan in the data of the Akino Giant Air Shower Array, known as AGASA. For years, this meticulous observatory scanned the skies, cataloging the impacts of these cosmic bullets. Then, researchers noticed something extraordinary. A small cluster of the very highest energy events seemed to be arriving from the same general patch of sky. This was not a single impossible particle, but a potential pattern, a cosmic whisper suggesting a specific address in the universe. The excitement among physicists was electric. Could this finally be the long-sought source, a single, monstrous object firing these rays directly at Earth? The idea of a hotspot was a beacon of hope in a field defined by randomness. Instead of 1,000 puzzle pieces scattered across the cosmos, here was a handful that seemed to fit together. But hope soon met the hard realities of statistics and probability. The universe is vast, and cosmic rays arrive in a seemingly random downpour. When you have a finite number of events plotted on an immense celestial map, small clusters can appear purely by chance. It is like sprinkling a handful of salt on a black tablecloth. Even if you toss the salt randomly, a few grains will inevitably land close together, creating the illusion of a small pile. The scientific community was divided. Was the AGASA cluster a true signal, or just one of these random cosmic salt piles? The debate could only be settled with one thing: more data. As years passed and newer, larger observatories like the Pierre Auger Observatory collected their own immense catalogues of events, the picture changed. The tantalizing AGASA hotspot began to fade, its constituent events lost in a broader, more diffuse map of arrivals. The cluster, it seemed, was almost certainly a statistical fluke. This episode is a perfect illustration of the profound challenge in this field. The clues are maddeningly subtle, and the universe is a master of deception. A promising pattern emerges, offering a potential key to the entire mystery, only to dissolve back into noise when examined more closely. It shows just how difficult it is to pinpoint a source when you are dealing with such rare, high-energy projectiles that are subtly bent by magnetic fields on their long journey. The search for answers continues, but it is a search where every potential breakthrough must first survive the ruthless test of probability. Another puzzle arrived from the Utah Desert, captured by the watchful eye of the high-resolution fly's eye detector. This experiment was a technological marvel designed to operate in stereo vision. It used two separate sites miles apart to observe the same cosmic ray shower from different angles, creating a three-dimensional picture of the event for unparalleled accuracy. But sometimes a single sight would capture something extraordinary on its own, a monocular event of such clarity and power that it demanded attention. One such event stood out, a cosmic ray with energy soaring well beyond 100 electron-volts. The detector worked by capturing the faint ultraviolet fluorescence light that is emitted as a particle shower develops in the atmosphere. It is not looking for the particle itself, but for the ghostly glow of its death throes. For a monocular event, scientists cannot triangulate its exact development path with the same precision as a stereo observation. Yet, by analyzing the specific shape and timing of the light curve it recorded, they could still make a reliable estimate of its colossal energy and its general arrival direction. This particular event was a clean signal, a high-fidelity recording of an impossible particle. Its energy was undeniable, placing it firmly in the category of phenomena that break the UHECR cutoff. More importantly, when its direction was plotted on the celestial map, it pointed to yet another unremarkable void. It was not from the same region as the Oh My God particle or the Yakutsk event. It came from its own unique and empty corner of the sky. This single data point and others like it contributed to a much larger and more profound realization. These ultra-high energy cosmic rays were not all coming from one place. They were not being fired from a single, dominant cosmic cannon in our galactic neighborhood. Instead, they were arriving from all over the sky, a random and isotropic distribution that suggests either there are many such sources scattered throughout the universe, or that the particles are being scrambled so completely by magnetic fields on their journey that their original directions are lost. The high-res monocular event was another vital piece of evidence confirming that the mystery was not localized. It was universal, a fundamental feature of the cosmos that we are only just beginning to perceive. Even the most powerful observatory on Earth was left staring into an empty void. The Pierre Auger Observatory sprawls across the Argentine pampas, a monumental scientific instrument covering an area larger than the city of Paris. Its design is a masterpiece of redundancy, employing two distinct methods to capture the truth about these cosmic invaders. 1,600 massive water tanks sit patiently under the open sky, waiting for the faint blue glow of Cherenkov radiation as secondary shower particles zip through their purified water. Meanwhile, 4 sets of fluorescence telescopes placed at the edges of the array constantly scan the atmosphere for the faint ultraviolet light these showers emit. This hybrid approach gives scientists a stereoscopic, cross-checked view of each event, creating what should be the most definitive cosmic ray map ever made. Yet, for one particular ray of immense energy, this precision only deepened the mystery. Every tank and every telescope agreed on the particle's staggering power and its precise trajectory through the cosmos. Researchers eagerly traced its path backward, expecting it to lead to a brilliant quasar, a swirling galaxy merger, or the supermassive black hole of an active galactic nucleus. They found nothing. The path ended in a vast, dark tract of intergalactic space, a celestial desert devoid of any known object capable of such violence. This event earned a telling nickname among the researchers who studied it, the pointless ray. It was a cosmic bullet fired from an empty gun. The Auger Observatory's immense power was supposed to eliminate uncertainty, to finally point a decisive finger at a source. Instead, its very precision confirmed a more unsettling reality. The emptiness is not an error in our measurements, it is a fundamental feature of the puzzle. The accelerators for these particles are either so well hidden that they emit no other trace we can detect, or they represent a form of astrophysics we have not yet even begun to imagine. How many more of these pointless messengers are traveling toward us, each one a perfect signal pointing directly to nowhere? Deep in the southern hemisphere, a cosmic cannonball struck with such force it lit up the sky for the Pierre Auger Observatory. This was not a faint whisper of an event. It triggered 120 of the observatory's water tank detectors simultaneously, a sprawling echo of a single catastrophic impact high in the atmosphere. The data painted a stunningly clear picture. The cascade of secondary particles, the air shower, developed with a specific profile and depth that allowed scientists to estimate not only its colossal energy, well over 200 exaelectron volts, but also the identity of the primary bullet itself. The evidence strongly suggested this was a nucleus of nitrogen, a middleweight atom that had been stripped bare and accelerated to a velocity approaching the speed of light. For physicists, an event of this quality is a scientific gold mine. It provides a pristine laboratory for studying hadronic interactions, which are the fundamental forces that govern the behavior of subatomic particles, at energy levels millions of times higher than anything we can create in particle colliders like the Large Hadron Collider. It is like having a front-row seat to the most violent particle physics experiment imaginable, one orchestrated by the cosmos itself. We can test our theories against its clean, unambiguous signal, refining our understanding of the very building blocks of reality. Yet, this incredible wealth of data also highlights a profound and frustrating paradox. We can dissect the moment of impact in exquisite detail. We know what the particle was, how much energy it carried, and precisely how it disintegrated. But all that brilliant forensic work leads to a complete dead end the moment we look backward along its path. The trajectory, calculated with the Auger array's renowned precision, points unerringly into another stretch of cosmic emptiness. We are left with a perfect understanding of the messenger and absolutely no clue who sent it. How can we know so much about the particle itself, yet remain entirely in the dark about the cosmic engine that created it? This particular cosmic ray seems to have ignored the universe's grand design. The monumental Pierre-Auger collaboration had painstakingly mapped the arrival directions of countless cosmic rays, and they found a whisper of a pattern, a faint statistical hint known as an anisotropy. On the largest scales, there appeared to be a slight correlation, a tendency for these ultra-high-energy particles to arrive from the general direction of the mass in our local universe, the nearby galaxies that form the cosmic web around us. It was a tantalizing clue, suggesting that the sources of these rays might be traced to the known structures in our celestial neighborhood. But then there are events like this one, the anisotropy differs. This specific cosmic ray arrived from a part of the sky that completely breaks that pattern, a direction that shows no enhanced density of galaxies, no concentration of matter that the Auger map would predict. It is a cosmic rebel that went off script. This presents a profound dilemma for scientists. Charged particles like protons are not like photons of light which travel in perfectly straight lines. They are deflected by the weak but pervasive magnetic fields that fill the space between galaxies. Think of these fields as a vast, invisible maze. Our models of this maze predict how much a particle should be bent from its original path over millions of light years. If a particle arrives from a direction that makes no sense according to our galactic map, it could mean one of two things. First, our models of these extragalactic magnetic fields could be completely wrong. Perhaps the fields are far stronger or more tangled than we ever suspected, scattering the particles so severely that their true origins are hopelessly scrambled. Or second, and even more intriguing, it could mean that there is not one single type of cosmic accelerator, but many. Perhaps some sources are indeed located within the nearby galaxies Auger sees a hint of, while other, even more mysterious sources are scattered randomly throughout the empty voids, firing their impossible bullets from the cosmic darkness. This single defying ray shatters the hope for a simple, unified answer, forcing us to consider that we are not hunting one monster, but an entire zoo of invisible cosmic beasts. Another cosmic ray struck from an unexpected direction, skimming the crowded plain of our own Milky Way galaxy. This is the realm of local cosmic traffic, filled with the steady drizzle of lower energy particles accelerated by supernova remnants and pulsars within our galactic neighborhood. For scientists, an ultra-high-energy event from this region creates an immediate and profound puzzle. The leading theory suggests that the most powerful cosmic rays come from far beyond our galaxy, from violent extragalactic sources. These should appear roughly equal from all directions, an isotropic distribution across the sky. A particle arriving from the galactic plane, however, blurs this clean distinction. It could be a genuine extragalactic traveler that just happens to have a flight path that aligns with the Milky Way's disk. Or, more troublingly, it could be a rare, high-energy outlier from a known galactic source, a local particle that somehow achieved an impossible speed. Distinguishing between these two possibilities is one of the most delicate tasks in cosmic ray astronomy. The properties of this particular low-inclination intruder made the puzzle even sharper. Its energy was perched right on the edge, arguably too high for any known process within our galaxy to produce. Imagine a local factory that usually makes firecrackers suddenly producing a weapon of mass destruction. Our galactic accelerators, like supernova shockwaves, are simply not thought to be potent enough to launch a single particle to such an extreme velocity. Yet there it was, this event forced physicists to ask a difficult question. Are we missing a new, hyper-energetic phenomenon hiding in plain sight within the Milky Way? Or is this just a cosmic coincidence, a true extragalactic giant masquerading as a local? The answer remains locked within the particle's faint signal, a reminder that sometimes the most confusing clues are found not in the deep voids, but right in our own crowded cosmic backyard. The 10th cosmic ray presents a puzzle not of power but of substance. Its fingerprint, captured by a sprawling observatory, revealed it was likely not a simple proton, but something far more substantial, a heavy nucleus like iron or nickel. How can scientists possibly know what a single, vanished particle was made of? The answer lies in the atmosphere itself. When a cosmic ray strikes the air, it creates a cascade of secondary particles, a sprawling avalanche known as an air shower. The key measurement is the depth at which this shower reaches its maximum number of particles, a parameter called X-max. Think of it like two different objects thrown into a pool. A lightweight ping-pong ball will skim the surface, creating a small, immediate splash. A heavy bowling ball will plunge deep before displacing a huge volume of water, creating a powerful surge from the depths. A proton is the ping-pong ball. It interacts quickly, creating a shower that develops high in the atmosphere. A heavy iron nucleus, however, is the cosmic bowling ball. It plows much deeper into the air before finally fragmenting in a dramatic, late-developing shower. The X-max measurement for this event pointed unequivocally to a heavy composite traveler. This single piece of information transforms the mystery into something even more baffling. Accelerating a heavy nucleus to such unbelievable speeds is a far greater challenge than launching a single proton. A proton is a simple, rugged speck, but an iron nucleus is a complex, fragile clump of 56 protons and neutrons. To hurl this entire assembly to nearly the speed of light requires an accelerator of almost unimaginable force and stability. And that is only the first problem. The journey itself is an even greater threat. The universe is filled with that thin, pervasive fog of cosmic microwave background radiation. For a heavy nucleus, this fog is not just a minor inconvenience. It is a relentless blasting sand of high-energy photons. Each collision acts like a hammer blow, chipping away at the nucleus, stripping off pieces, and eventually shattering it into a cloud of simpler protons and neutrons. An iron nucleus traveling across millions of light years should be utterly disintegrated long before it ever reaches our detectors. The fact that this one arrived intact, carrying its immense energy, forces a staggering conclusion. Its source cannot be very far away. It must be relatively local within our own galactic neighborhood or a nearby galaxy to have survived the trip. Yet, just as with the others, when we look back along its path, we find no suitable local source capable of such a feat. We are left hunting for a hidden cosmic forge, one that can not only create unimaginable power but also forge and deliver impossibly heavy bullets across space. Just as we begin to accept the idea of heavy cosmic bullets, the universe sends us a lightweight messenger. The 11th cosmic ray was a classic, a particle that all the evidence suggests was a simple, solitary proton. In the vast catalogue of ultra-high-energy events, this one behaved like a pure, fundamental speck of matter. When a proton slams into the atmosphere, it creates a very specific kind of air shower. Unlike the deep, plunging cascade of a heavy nucleus, a proton interacts almost immediately. It creates a shower that develops higher up, spreading its secondary particles over a wider area in the upper air. It is the difference between a bowling ball creating a deep, concentrated surge and a precisely shattered marble scattering its fragments in a broad, shallow pattern. This high-flying, sprawling cascade is the unmistakable signature of a proton, but this clarity only introduces a new layer of confusion. A proton, being a single, charged particle, is incredibly susceptible to the magnetic fields that fill the space between galaxies. Think of these fields as a complex, invisible network of winding roads. A heavy nucleus with its greater mass and multiple charges is like a heavy truck that resists being pushed off course by a strong crosswind. A proton, however, is like a lightweight leaf, tossed and turned with every subtle magnetic gust it encounters on its million-light-year journey. For scientists trying to trace this proton-like ray back to its source, this is a devastating problem. The direction from which it arrived is almost certainly not the direction of its origin. Its path has been scrambled, bent, and twisted so many times that its arrival point is essentially a random landing spot on our celestial map. It points nowhere. This creates a fundamental paradox in our search for answers. We can be more confident about what this particle was, but we have far less confidence about where it came from. This single event highlights the maddening composition problem at the heart of ultra-high-energy cosmic rays. The cosmic rays arriving at Earth are not a uniform army. They are a mixed bag, a chaotic assortment of lightweight protons, middleweight nuclei like nitrogen, and heavyweights like iron. Each type tells a different story about its origin and its journey. A heavy nucleus suggests a nearby source, as it could not survive a long trip. A proton could have come from almost anywhere in the universe. The problem is that we do not know the mix. We do not know if most of these rays are protons or iron or something in between. Each new event, like this proton-like puzzler, adds another piece to the puzzle, but we are still missing the box lid that shows us what the final picture is supposed to be. Are we seeing the diverse output of a single type of cosmic accelerator, or are we collecting messages from many different kinds of monsters, each with its own unique way of forging impossible projectiles? Sometimes the cosmos seems to send us a clear signal, only to snatch it away a moment later. A pair of ultra-high-energy cosmic rays struck Earth within a remarkably short time of each other, both arriving from an indistinguishable patch of sky. These were not just any two particles. Each carried an energy that should not exist, and their sequential arrival from the same cosmic address sent a jolt of excitement through the scientific community. The probability of two such rare, catastrophic events originating from the same small region of space by pure chance is astronomically low. It felt like receiving two certified letters in a row from the same unknown sender. Could this finally be the long-sought repeating source, a single cosmic engine firing multiple bullets directly at us? The hunt began immediately. Astronomers swung every available eye toward that region of the sky. They searched with optical telescopes for a brilliant galaxy, with radio telescopes for the scream of a jet from a black hole, and with X-ray and gamma-ray observatories for the signature of violent, high-energy processes. They scanned the entire electromagnetic spectrum, searching for any flicker, any anomaly, any clue that could explain the twin events. They found nothing. The patch of sky was quiet, dark, and utterly ordinary. This profound silence revealed a crucial and daunting aspect of the mystery. The source, whatever it was, must be transient. It is not a constantly shining beacon, but a cosmic flashbulb that ignites for a brief, violent moment to accelerate a single particle to impossible speeds, and then shuts off completely, leaving no trace. It might be a sporadic explosion, a sudden magnetic reconnection, or a catastrophic stellar collision that occurs in an instant and then fades into darkness. The challenge this presents is immense. We are trying to catch a cosmic sniper who fires a single, impossibly powerful shot and then vanishes without a whisper, leaving only the faint echo of the bullet for us to find. How can we ever hope to understand the gun if we can never see it fire? The 13th cosmic ray offered a tantalizing false lead, its trajectory seemingly pointing straight back to the heart of our own galaxy. Imagine tracing the path of a celestial bullet and finding it leads directly to the most violent and chaotic place in our Milky Way, the galactic center. There, shrouded in dust and brilliant star clusters, lurks Sagittarius, a star, the supermassive black hole anchoring our entire galaxy. It is a natural suspect, a gravitational monster with the raw power to tear stars apart. For a moment, it seemed we might have found our culprit, a cosmic cannon in our own backyard. Yet, this promising lead quickly unraveled upon closer inspection. Sagittarius, a star, is, by the standards of supermassive black holes, remarkably quiet and dormant. While it possesses the potential for immense violence, it is not currently producing the kind of energetic jets or outbursts we see in active galactic nuclei in other galaxies. It is a sleeping giant, not a raging one, but there is an even more fundamental reason this ray could not have come from there. The galactic center is a tangled knot of immensely powerful magnetic fields. Think of these fields as an inescapable prison for charged particles. Any particle accelerated to high energy near Sagittarius, a star, would not fly freely out into the cosmos. Instead, it would be caught in a chaotic magnetic maze, forced to spiral endlessly until it lost all its energy, trapped forever near the place it was born. For a particle to reach Earth with the energy we observed, it would have had to perform an impossible escape from this magnetic fortress. So if the ray did not come from the galactic center, why does it point there? The answer lies in the long and winding journey through our galaxy's magnetic web. That single, straight line we draw on a map is a profound oversimplification. A charged particle does not travel in a straight line. It is constantly deflected, bent, and corkscrewed by every magnetic field it passes, from the faintest interstellar breeze to the vast galactic currents. The apparent origin at the galactic center is most likely a cosmic mirage, a final deflection that makes it look like the particle came from there, when in reality its true source could be anywhere in the sky. This misdirection is a crucial lesson in cosmic humility. It reminds us that the universe is not a simple shooting gallery, and these particles are not bullets flying in clean, straight paths. They are more like messages passed through a complex, invisible labyrinth, their contents intact but their return address hopelessly scrambled. How many other cosmic rays are pointing us in completely the wrong direction, sending us on wild goose chases while their true origins remain hidden in the dark? This 14th cosmic ray was a true void wanderer, a messenger from absolute nothingness. Its trajectory, calculated with painstaking precision, pointed backward into one of the vastest empty regions in the observable universe, a cosmic void spanning hundreds of millions of light years. These are not just empty patches of sky. They are the universe's true deserts, immense volumes of space where the density of galaxies plunges to almost zero, where matter is so scarce that these regions are mostly just space. Finding an ultra-high-energy cosmic ray from such a place is like finding a lit match at the center of an empty, darkened aircraft hangar. There is simply nothing there to light it. This presents a problem so profound it threatens to break our entire understanding of astrophysics. Every known cosmic engine, from supermassive black holes to colliding galaxies, requires immense concentrations of matter and energy to function. A void has none of that. It is the antithesis of a power source. So how did this particle get its staggering energy? The void itself offers no answers, only a deeper, more unsettling question. One radical explanation now forces its way into the conversation, a concept that steps beyond stars and galaxies and into the shadowy realm of particle physics. Perhaps the source is not a cosmic object at all, but a form of matter we cannot see. Scientists have long hypothesized the existence of super-heavy dark matter, theoretical particles left over from the Big Bang that are billions of times more massive than a proton. These hypothetical behemoths would be unstable, and their decay over eons could release a tremendous burst of energy, creating a single, ultra-high-energy cosmic ray as a final product. The crucial detail is that dark matter is not concentrated in galaxies alone. It forms a vast, invisible scaffold throughout the entire cosmos, permeating the voids as well as the clusters. If these super-heavy particles exist, they will be decaying everywhere uniformly in the crowded galactic cities and in the deepest, darkest cosmic countryside. This single void wanderer is a direct, tantalizing piece of evidence for this exotic idea. It is a signal from the dark, invisible fabric of the universe itself, a potential whisper that the answer to our greatest cosmic mystery has been hiding in plain sight all along, woven into the empty spaces between everything. A cosmic ray arrived from the direction of a bustling galactic city, a massive cluster of thousands of galaxies bound together by gravity. This seems like the perfect culprit. Galaxy clusters are among the most violent environments we know, filled with superheated plasma, colossal shock waves from merging galaxies, and turbulent magnetic fields that stretch across millions of light years. In theory, these conditions are a perfect cosmic particle accelerator. The immense shock waves ripping through the cluster should be able to slingshot protons and other nuclei to incredible speeds, just like a surfer getting repeatedly pushed by a perfect wave. For a moment, it appears the mystery is solved, but the theory collides with harsh reality on two critical fronts. First, those same powerful magnetic fields that accelerate particles also act as a nearly inescapable prison. A particle might get a tremendous boost of energy, but it then becomes trapped, forced to spiral endlessly along magnetic field lines within the cluster. It cannot break free to begin the long journey to Earth. For a cosmic ray to reach us, it must perform a miraculous escape from this magnetic labyrinth, a feat that current models struggle to explain. The second problem is even more direct. The energy of this particular cosmic ray was simply too high. Even the most optimistic calculations for shock acceleration within a galaxy cluster fall short of the monstrous energies we detect. It is like discovering a local factory can produce powerful fireworks, but then finding a stick of dynamite on your doorstep with its return address. The factory might be capable of impressive things, but it cannot account for the sheer destructive power you are holding in your hand. This cluster contradiction highlights a frustrating and recurring theme. The universe presents us with a plausible suspect, a known violent phenomenon that seems to fit the profile, only for the forensic evidence to not match up. We are left knowing that these clusters are indeed powerful accelerators, but they seem to be producing the wrong kind of ammunition, or they are unable to deliver it to our doorstep. The search continues not for a lack of candidates, but for a source that can overcome both the prison of magnetic fields and the fundamental limits of energy itself. Another event stands out not for its raw power, but for its deeply controversial identity. Some researchers analyzing the data from a particular ultra-high-energy impact claim the primary particle was not a proton or a nucleus, but an ultra-high-energy photon. If true, this would have been one of the most significant discoveries in modern astrophysics. A photon is a particle of light, neutral and untouched by the magnetic fields that so hopelessly scramble the paths of charged particles. It would have flown across the universe in a perfect, unwavering straight line, its arrival direction pointing like a flawless cosmic arrow directly back to its source. After decades of searching through a scrambled maze, this would have been the clean address we were desperate to find, but the implications run even deeper. The existence of a photon at such an extreme energy would shatter known physics in another way. The entire cosmos is filled with the radio and infrared glow of background radiation. For an ultra-high-energy photon, this faint light acts like a thick cosmic tar. According to our well-tested theories, such a photon should interact with this background radiation over relatively short distances, creating pairs of electrons and positrons and bleeding away its energy long before it could ever traverse intergalactic space. Detecting one of these photons would mean our understanding of how light and matter interact at the highest energies is fundamentally wrong. This single claim ignited a firestorm of debate within the scientific community. The core of the controversy lies in a maddeningly difficult challenge, telling the difference between a shower created by a photon and one created by a proton when all you see is the aftermath in our atmosphere. Both can produce cascades that look remarkably similar in a detector. Scientists look for subtle clues like the number of muons in the shower or the exact shape of its development, but these signatures are fuzzy and open to interpretation. One team's clear photon signal is another team's unusual proton. The debate over this event raged in conference halls and scientific papers, a fierce battle over the interpretation of a single, faint signal. In the end, the claim could not be definitively proven. It remains a tantalizing, unresolved question, a ghost in the data. It teaches us a humbling lesson. Even when the universe seems to offer us a perfect clue, our tools and our theories may not yet be sharp enough to read it. The 17th cosmic ray was a perfectly captured enigma. Recorded by the Pierre Auger Observatory, this event was a data analyst's dream. Its energy was immense, its air shower profile was textbook, and its trajectory was calculated with the observatory's renowned precision. Every detector that saw it told the same clean, unambiguous story. Yet, when all the numbers were crunched and the maps were drawn, the result was a scientific nothing burger. It told researchers absolutely nothing they did not already know. It was just another ultra-high-energy particle from another unremarkable patch of empty sky. This is the quiet, unglamorous reality of the search. For every oh my god particle that shatters paradigms, there are dozens of these impeccably recorded, utterly baffling normal events. They are the background noise of the cosmic mystery. This highlights a fundamental challenge in the field, the bandwidth problem. Our most advanced observatories can only capture a handful of these rare, top-tier events each year. Each one is a precious data point, and we pour immense resources into analyzing it, hoping for a breakthrough. But most of the time, the result is simply another dot on a map that already looks hopelessly random, another data point that fits perfectly within the known, confusing population of cosmic rays. These normal mystery events are the statistical bedrock of the entire field. While they do not provide flashy headlines, they are quietly building up the average properties of the ultra-high-energy cosmic ray population. They help scientists define the typical energy, the common arrival directions, and the overall mix of particles. This growing statistical profile is a powerful tool for weeding out theoretical models. A new theory might perfectly explain one or two spectacular events, but does it also account for the 100 other normal ones? If it does not match the broader statistical distribution, the model fails. So these seemingly uninformative events act as a cosmic reality check. They force theorists to confront the entire messy picture, not just the most dramatic outliers. They are the constant, humbling reminder that the universe's deepest secrets are not always revealed in a single, brilliant flash, but are often hidden in the patient, painstaking accumulation of perfectly measured, perfectly ordinary mysteries. Another cosmic sentinel stationed in the northern hemisphere recorded its own impossible event. The telescope array, gazing up from the Utah Desert, captured a cosmic ray with an energy that would be a perfect twin for many of the events seen by its southern counterpart, the Pierre Auger Observatory. The raw power was the same, a force that defies the GZK cutoff, but the story it told was subtly different. When scientists compared the maps from the two great observatories, a crucial question emerged. Does the sky of ultra-high energy cosmic rays look the same from every vantage point? For the first time, we could compare the view from the northern and southern hemispheres, like having two witnesses describing the same crime from opposite sides of the room. Their testimonies must agree for the story to hold. This particular northern ray and others like it are vital pieces in that cosmic cross-examination. The Auger Observatory, from its unique position in Argentina, sees a sky dominated by the dense, nearby mass of our local universe, the supercluster of galaxies we call home. Its data hints at a faint, large-scale anisotropy, a slight excess of arrivals from that general direction. But what does the telescope array see from the north? Its patch of the sky looks out toward a much sparser cosmic neighborhood, a quieter celestial suburb. If the northern sky shows a completely different pattern or no pattern at all, it would mean the sources are not uniformly distributed. Some cosmic accelerators might be hidden in the southern sky, completely invisible to the northern instruments, and vice versa. This is the fundamental power of full sky coverage. You cannot understand a global phenomenon by only looking out your front window. You need to see the entire planet. A source could be firing its rays directly at the southern hemisphere, and we in the north would be completely blind to its existence. The data from this northern sentinel is a crucial check on our theories. It helps answer whether we are surrounded by a uniform fog of these events, or if we are in the crosshairs of a few specific, hidden monsters whose location we can only pinpoint by seeing the whole sky. Each new event from the telescope array is not just another dot on a map. It is a vote in a cosmic election, helping to decide if the universe is filled with a random drizzle of these particles, or if they are arriving from a handful of secret addresses we have not yet learned to read. Sometimes the most precise measurement only deepens the mystery. The 19th cosmic ray was captured in a flash of ultraviolet light, its entire death plunge recorded by the fluorescence detectors of the Pierre Auger Observatory. This gave scientists something truly special, a pristine view of the shower's longitudinal development. This is the gold standard of energy measurement, a technique so reliable it is known as calorimetry. Imagine trying to measure the power of an explosion by studying the exact shape and size of the fireball as it expands, rather than just listening for the boom. That is what calorimetry does for a cosmic ray. By tracking how the cascade of particles grows and then fades as it plunges through the atmosphere, physicists can calculate the primary particle's initial energy with an accuracy of just a few percent. There is no guesswork, no ambiguity. We know exactly how much energy this cosmic bullet carried when it struck our air, and that number was, as always, impossibly high. Yet this supreme confidence in the what is met with absolute ignorance of the where. The trajectory, calculated from the same exquisite data, pointed back into yet another stretch of intergalactic emptiness. It is the ultimate scientific tease, a perfect answer to one question that only highlights our complete failure to answer the others. We are handed a cosmic autopsy report of unparalleled detail, describing the victim and the exact force of the impact, while the case of the unknown assailant remains utterly cold. This is the fundamental disconnect at the heart of the search. We have mastered the art of forensics for these events, yet we are no closer to finding the criminal. How can we know so much about the moment of impact and still know nothing about the shooter? This 20th cosmic ray is a master of misdirection, its true origin hopelessly lost in a labyrinth of invisible force. Unlike a photon of light that travels in a perfectly straight line, a charged particle like a proton is a slave to magnetism. It does not fly, it spirals, caught on the endless, twisting highways of galactic and extragalactic magnetic fields. Imagine trying to trace the path of a single, lost marble as it ricochets through an immense, dark, and complex pinball machine. You see where it finally emerges, but the path it took to get there is a complete mystery. This is the fundamental frustration of tracing this particular cosmic ray. We know where it landed, but we have no idea where its journey began. The weak but pervasive magnetic fields that fill the space between galaxies act like a cosmic blender, thoroughly scrambling the directions of these particles over millions of light years. A particle that started its life heading directly for one star system could be deflected so many times that it ends up arriving at another, its original address erased by the journey. This single event perfectly illustrates the monumental challenge at the heart of ultra-high-energy cosmic ray astronomy. We can build bigger and better detectors to catch more of these particles, but for most of them, the very act of catching them does not tell us where they came from. The magnetic maze ensures their paths are chaotic and unpredictable. This profound limitation has forced scientists to change their entire strategy. If we cannot trust the twisted paths of charged particles, we must search for neutral messengers, cosmic couriers that are immune to these magnetic fields. The dream is to find an ultra-high-energy neutrino or a gamma-ray photon arriving from the same direction as one of these cosmic rays. A neutrino, a ghostly particle with almost no mass and no charge, would slice through the magnetic maze completely unaffected, pointing a flawless arrow back to its source. A gamma-ray photon, though it can be absorbed by other light, would also travel in a pristine straight line. Catching a neutral messenger in tandem with a cosmic ray would be the ultimate breakthrough, finally giving us a clean address for the cosmic canon. Until that day, however, we are left with countless magnetic maze runners, each one a perfect signal pointing directly to nowhere. Far out in the energy spectrum of the cosmos lies a strange and telling feature known as the NE. The entire cosmic ray energy spectrum is not a smooth line, but a road with dramatic twists and turns. Picture a graph where the energy of cosmic rays climbs from left to right. At first, the number of rays is incredibly high, a torrent of low-energy particles constantly raining down on us. But as you follow the line to higher energies, it begins to plummet steeply. The point where this plunge becomes most dramatic is called the NE, a bend in the graph around 1 million times the energy of particles in the Large Hadron Collider. Beyond this point, cosmic rays become exponentially rarer. Then, at energies 1,000 times higher still, the graph flattens out again at a feature called the ankle, marking the beginning of the ultra-high-energy regime we have been exploring. The NE has long been thought of a boundary, an energy wall beyond which our local galactic accelerators, like supernova remnants, simply cannot push particles. It is the dividing line between the common galactic drizzle and the rare extragalactic storm. But the 21st cosmic ray is a confuser, an event that lands right in this problematic transitional zone. Its energy is not quite in the ultra-high-energy realm that defies all physics, but it is far beyond the NE, sitting in a strange and sparsely populated no-man's land. This specific energy makes it profoundly difficult to classify. Is it a runaway from our own galaxy, a super-powered outlier that somehow got an extra boost from a local supernova? Or is it a weak, low-energy cousin of the monstrous extragalactic rays, a mere whisper from a distant cannon whose full power we cannot see? Its ambiguous position challenges the very idea of a simple, two-population model for cosmic rays. We want a clean story, one where galactic sources produce all the rays up to the NE and extragalactic sources take over beyond the ankle. This confuser ray blurs that clean line into a messy, uncertain gray area. It suggests that the cosmic ray population is not a binary choice but a complex and overlapping mix. Perhaps there are multiple types of accelerators at work within our galaxy, some capable of occasionally punching a particle far beyond the expected limit. Or maybe the extragalactic sources themselves produce a wide range of energies, and this ray is simply at the low end of their incredible output. This single, problematic energy measurement forces us to admit that the universe does not respect our neat categories. The boundary between local and distant, between possible and impossible, is far more porous and mysterious than we ever imagined. Our own star can sometimes mimic the violence of deep space. The Sun constantly exhales a stream of charged particles known as the solar wind, and its magnetic field, stretching far beyond Pluto, creates a protective bubble called the heliosphere. For the common, lower-energy cosmic rays that constantly rain down on us, this solar activity acts as a powerful modulator. When the Sun is active with increased sunspots and solar flares, its intensified magnetic field and wind push back against these incoming low-energy particles, reducing their numbers at Earth. It is a celestial weather system where a stormy sun shields us from some of the local cosmic drizzle. But then there is the 22nd cosmic ray, an event recorded during a profound solar minimum, a time when our star was exceptionally quiet and calm. Its detection during this solar lull is a crucial piece of forensic evidence. The unimaginable energy this particle carried placed it in a category all its own. The Sun's magnetic influence, so effective at deflecting low-energy rays, is utterly insignificant against such a projectile. Think of it like trying to stop a cannonball with a gentle breeze. The solar wind and its associated fields have no more effect on an ultra-high-energy cosmic ray than a mosquito would have on a bullet train. This quiet sun event therefore rules out any possibility of a local solar system origin. It was not a rogue particle from our own star or one deflected by its magnetic weather. This confirmation is both humbling and awe-inspiring. It means that this specific particle, and by extension all its ultra-high-energy kin, began its journey in the true depths of interstellar or even intergalactic space. It is a pure, untainted messenger from the cosmic void, its signal completely unaffected by the petty magnetic storms of our own celestial neighborhood. Every time we detect one of these colossal events, we are receiving a communication that has traveled for millions, perhaps even billions of years, completely untouched by the trivial influences of our solar system. The 23rd cosmic ray triggered a massive hunt across the entire spectrum of physics. When this ultra-high energy particle was recorded, astronomers did not just note its arrival, they launched a full-scale multi-messenger investigation. This powerful approach is the great hope of modern astrophysics, the idea of cosmic triangulation. Instead of relying on a single, scrambled signal, scientists combine different types of cosmic messengers, each telling a different part of the story. They search for a flash of gamma rays, a burst of optical light, a whisper of radio waves, or the ghostly passage of a neutrino, all arriving from the same patch of sky at roughly the same time as the cosmic ray. Finding a match would be the ultimate breakthrough, a perfect fingerprint left at the scene of the cosmic crime. For this particular event, the global network of telescopes and neutrino detectors swung into action, scanning the arrival direction for any hint of a simultaneous explosion. They found nothing. The void was silent. There was no gamma-ray burst, no supernova flash, no anomalous neutrino count. This profound silence, this multi-messenger non-event, was itself a crucial piece of data. It actively ruled out entire classes of cosmic catastrophes as the source for this particle. Certain types of long-duration gamma-ray bursts, which are the death cries of massive stars, would have produced a brilliant and unmistakable flash of light that our satellites would have surely seen. Powerful supernova, the violent end of white dwarfs, would have left a similar electromagnetic signature. The fact that we saw absolutely nothing means this cosmic ray could not have been born in those specific, well-understood types of stellar explosions. Sometimes what you do not see is as important as what you do. This non-detection forces the mystery into a darker, more exotic corner. It suggests the accelerator for this particle must be a truly dark engine, one that can unleash unimaginable force without the brilliant fireworks we have come to expect from the universe's most violent events. It operates in total secrecy, leaving behind only a single, impossibly energetic bullet as its sole calling card. The 24th cosmic ray refused to fit into any of our established boxes. When it tore through the atmosphere, its cascade of particles developed at a depth that was deeply puzzling, a measurement that sat awkwardly between the expected profiles for a lightweight proton and a heavy iron nucleus. It was as if the universe had fired a particle that was neither a ping-pong ball nor a bowling ball, but something entirely different. This strange atmospheric fingerprint points directly to the frontier where astronomy meets the most fundamental particle physics. The models we use to understand these air showers are based on hadronic interactions, the complex rules governing how particles like protons and neutrons collide and fragment. These rules are tested and proven in our powerful particle colliders here on Earth, but there is a catch. The energies involved in this cosmic ray impact were millions of times higher than anything our most advanced machines can produce. We are venturing into an energy frontier that is completely uncharted by laboratory science. So what does this mean? The unusual depth of this shower could be a tantalizing whisper of new physics. Perhaps at these extreme energies, particles interact in ways we have not yet discovered, shattering and spreading their energy in patterns our current models cannot predict. This single, anomalous event could be a crack in the foundation of the standard model of particle physics, a hint of laws that only reveal themselves under the most violent cosmic conditions. The other, more humbling possibility is that this was just a rare statistical fluke, a perfectly normal proton or iron nucleus that happened to develop its shower in an unusual way that merely looks strange to our instruments. Distinguishing between a true breakthrough and a simple fluctuation is the daily torment of researchers in this field. This cosmic ray, with its ambiguous profile, is a perfect symbol of that challenge. It represents a question we cannot yet answer with our current tools, a signal from the dark edge of our understanding where every new piece of data could either reveal a new universe of physics or simply fade back into the noise. Long before the "oh my God" particle shocked the world, a different kind of anomaly was detected in the New Mexico desert. The Volcano Ranch Array was a pioneering instrument, a simple grid of plastic scintillators spread across the barren landscape, waiting for the faint echoes of cosmic violence. In the 1960s, it recorded an event of staggering energy, a cosmic ray that should not have existed with the technology of its day. This was not a discovery met with immediate celebration, but with deep-seated skepticism. How could a humble array of detectors, a fraction of the sophistication of modern observatories, have stumbled upon something so profoundly powerful? The scientific establishment questioned the instrumentation, the calibration, and the very interpretation of the data. It seemed more likely that the result was a glitch, a product of wishful thinking, than a true window into an impossible universe. Yet the researchers stood by their findings. They had witnessed a ghost in their machine, a signal so strong it could not be easily dismissed. This historical detection, and others like it from that era, are the old guard of the cosmic ray mystery. They are the foundational proofs that this enigma is not a recent fluke of advanced technology. For decades, these stubborn signals have persisted, whispered from the void through increasingly sensitive instruments, each generation of scientists confirming what the last one found. The mystery has endured not because of our ignorance, but in spite of our growing knowledge. It has resisted every attempt at a simple explanation, outlasting the very detectors that first recorded it and the scientists who first dared to believe the data. These early events laid the unshakable groundwork for everything that followed, proving that the universe has been firing its impossible bullets at us for far longer than we have known how to listen. A century of technological progress separates the crude scintillators of Volcano Ranch from the digital sentinels of today. Our 26th cosmic ray was captured by a modern observatory's silicon brain, its entire demise recorded in picosecond precision. This was no faint echo. The particle's air shower was dissected by digital electronics that sampled data billions of times per second, mapping the cascade of secondary particles with a resolution that would have been pure science fiction for the pioneers. We can now watch the entire catastrophic event unfold in a digital slow-motion replay, tracing the birth, peak, and decay of billions of particles in our atmosphere. Every nuance of its violent death is laid bare in terabytes of flawless data. And yet, for all this technological majesty, the final line of the report reads exactly the same as it did 50 years ago. Point of origin unknown. This particle is a digital ghost, a phantom captured in ultra-high definition. Its passage is documented with an elegance that the old guard could only dream of, but its essence remains just as elusive. We have traded hissing analog signals for pristine digital streams, yet the core message from the cosmos is unchanged. The mystery has simply been upgraded to a higher resolution, proving that building a better microphone does not automatically make the universe speak any clearer. The void still holds its secrets, now just with more pixels. A cosmic arrow came screaming down from directly overhead, striking the atmosphere at a near vertical angle. This steep trajectory, known as a small zenith angle, is a rare gift for scientists. When a cosmic ray enters the atmosphere straight on, its resulting particle cascade plunges almost directly downward, creating a clean, symmetrical footprint on the ground that detectors can map with incredible precision. There is no messy, slanted path to untangle. For an event like this, every scintillator tank and fluorescence telescope sees a nearly perfect snapshot of the shower's development, from its first interaction high in the atmosphere to its final moments as it spreads across the desert floor. This 27th cosmic ray was a textbook case, a pristine laboratory for studying the intricate physics of an air shower. Its behavior from the moment it struck our air was flawless, matching every prediction from our most sophisticated models. We could use its signal to fine-tune our understanding of the atmosphere itself, calibrating how particles lose energy as they travel through different layers of air. This event was in essence a perfect known quantity, and that is precisely what makes its origin so deeply frustrating. We know everything about its death and absolutely nothing about its life. Its journey before that first fateful collision with an air molecule is a total black box. It behaved exactly as a proton or an iron nucleus should once it decided to end its voyage on our planet. But where did it come from? What unimaginable event gave it such speed? The perfect normalcy of its final moments offers no clues, only the maddening silence of the void it came from. We are left with a perfectly understood messenger who refuses to tell us who sent it. While one cosmic ray plunged straight down, another took the scenic route. This 28th messenger arrived at an almost horizontal angle, skimming the very edge of our atmosphere. Instead of a short, direct death, it traveled a vastly longer path through hundreds of miles of air. For scientists, this long, shallow journey is a double-edged sword. On one hand, it provides an unparalleled view of an air shower's complete life cycle. The cascade of secondary particles has immense space to develop, grow to its maximum size, and then slowly fade away, all while being tracked by a long line of detectors spread across the landscape. This extended development allows for a remarkably precise measurement of the primary particle's energy and composition, like watching an entire movie from start to finish instead of just seeing the final scene. Yet this incredible clarity comes with a heavy price. That long, vulnerable journey through the atmosphere is fraught with peril. The primary particle, or the shower it creates, has more opportunities to interact with air molecules, subtly changing its character. More critically, the weak but pervasive magnetic fields of Earth itself have a much greater opportunity to deflect the charged particles in the shower over that extended distance. Think of it like trying to trace a laser beam that has been bounced off a dozen slightly crooked mirrors. By the time the signal reaches your detectors, its original direction has been subtly but significantly scrambled. So while we get a perfect autopsy report on the particle itself, the long journey adds another layer of fog to the already difficult task of backtracking its cosmic origin. This horizontal surprise perfectly captures the fundamental trade-off in this field. Do we prioritize understanding the precise nature of the messenger, even if we lose its return address? Or do we focus only on the steeply falling events that give us a cleaner shot at finding the source, even if we know less about the particle itself? Every detection is a negotiation with the atmosphere itself, a choice between two different kinds of truth, and neither one gives us the complete picture we so desperately seek. Even the most advanced detector array can be caught off guard by a cosmic strike. Our 29th cosmic ray was an unlucky event, a near miss that hit the very periphery of a sprawling observatory. Only a handful of the hundreds of detectors registered its passing, capturing a faint, fragmented footprint of the immense air shower it created. This partial data is a scientist's nightmare. Reconstructing the true nature of a cosmic ray is like trying to identify an elephant by touching only its tail and one leg. With a full array trigger, you feel the entire animal, understanding its size, shape, and power. But with just a few scattered signals, the picture becomes a blur of possibilities. The energy estimate becomes a wide range, a guess rather than a measurement. The arrival direction, normally pinpointed with laser precision, becomes a fuzzy cone of uncertainty spanning a large swath of the sky. This unlucky event serves as a stark reminder of the immense practical challenges in this field. These cosmic bullets are incredibly rare, and we build monumental machines to catch them. Yet sometimes, when one finally arrives, it grazes the edge of our net, leaving us with a tantalizing but ultimately incomplete message. Its true energy might have been monumental or merely impressive. Its origin could have been a specific void or an entire quadrant of the universe. We will never know for sure. These partial captures add to the statistical noise, the background of uncertain events that researchers must carefully sift through, always wondering if the one that got away was the key to everything. This one cosmic ray was seen by two sets of eyes. Far apart on the Argentine plains, the twin fluorescence telescopes of the Pierre Auger Observatory, both locked onto the same faint ultraviolet glow blooming in the night sky. This was a stereo vision event, the gold standard of cosmic ray detection. When a single sight sees a shower, it is like looking at a photograph of a distant object. You can estimate its distance and size, but there is always some uncertainty. With stereo vision, it is like seeing the world with both eyes open, creating a perfect three-dimensional view of the particle's death plunge. The dual perspectives allowed scientists to triangulate the shower's core axis with pinpoint accuracy, tracing its path backward through the atmosphere with an error margin of less than a single degree. They could measure the exact depth where the cascade of particles reached its maximum, a crucial detail for identifying the primary particle's composition and calculating its initial energy with near-perfect confidence. This was not a fragment of a signal or a lucky guess. This was the cleanest, highest fidelity data imaginable, a pristine recording of an impossible event. Every detail of its catastrophic arrival was laid bare in the data, a perfect cosmic autopsy, and the report was definitive. The energy was colossal, well beyond the theoretical limit for long-distance travel. The trajectory was calculated with breathtaking precision, a single, sharp line drawn across the celestial sphere. That line pointed backward through the void and ended in absolute nothingness. No galaxy, no quasar, no dark cloud, just the empty vastness of intergalactic space. This stereo vision champion represents the ultimate paradox of this entire search. We have achieved a level of observational perfection that allows us to dissect these events with surgical precision. We know exactly what they are, how much energy they carried, and the precise path they took in their final moments. Yet for all that technical mastery, the origin remains a perfect blank. The universe has handed us a flawless message, written in a language we can now read perfectly, and the message itself is simply this: I am here, and you will never know from where. A cosmic ray arrives with a trajectory that does not point into the deep void, but instead aligns with the vast, invisible sphere surrounding our own Milky Way. This is the galactic halo, a sprawling cloud of dark matter, ancient stars, and lonely stellar remnants that envelops our entire galactic disk. While most theories point their fingers far beyond our galaxy, this particular messenger offers a compelling clue for a different story, one where the source of these incredible energies might be hiding much closer to home. The halo hypothesis is a less popular but stubbornly viable idea. It suggests we do not need to look millions of light years away for an answer. The accelerators could be right here in our own cosmic backyard, woven into the faint, extended fabric of our galaxy's outer reaches. What could possibly be out there in that dim and diffuse halo with enough power to launch a single particle to such impossible speeds? One leading candidate is the population of old neutron stars. These are the dense, collapsed cores of long-dead suns, spinning rapidly and possessing magnetic fields of unimaginable strength. A specific type known as a magnetar has a magnetic field so powerful it could, in theory, act as a natural particle accelerator of cosmic proportions. The twisting and snapping of these intense magnetic fields could generate enormous voltages, capable of ripping particles from the star's surface and hurling them across space like a slingshot. Another, more exotic possibility involves the halo's primary resident, dark matter. If this mysterious substance is made of certain theoretical particles, their mutual annihilations or decays in the dense halo could release bursts of energy, creating ultra-high-energy cosmic rays as a byproduct. This particular ray's energy and composition do not definitively rule out such a local galactic origin. Its properties are just ambiguous enough to keep the door open, a quiet reminder that the most dramatic solution is not always the correct one. Perhaps we are overcomplicating the mystery by gazing into the deepest voids, when the real culprit has been silently circling our own galaxy all along. This particle was a pure extragalactic champion, arriving with a trajectory that screamed it came from far beyond the Milky Way's crowded disk. Its path pointed away from the galactic plane into the deep, quiet darkness between galaxies. Its immense energy was the final seal on this verdict, a force so great that no known process within our own galaxy could have been its cradle. This ray embodies the dual identity of these cosmic messengers. They are subatomic particles, the domain of physicists, but their sources are colossal astronomical objects, the domain of astronomers. Studying them is the essence of astroparticle physics, a hybrid science that uses tiny particles to probe the largest structures in the universe. So we have our clear messenger from another galaxy, a cosmic postcard stamped with an intergalactic return address. But the address is tragically incomplete. The vastness of the space it crossed is almost beyond human comprehension. The potential source galaxy could be hundreds of millions of light years away, a faint, distant island of stars in an ocean of black. Searching for it is the ultimate cosmic needle in a haystack challenge. Imagine standing in a dark field at night, trying to identify which specific star a single, high-powered laser pointer was fired from, using only the final dot of light that hits your shirt. Our telescopes scan the arrival direction, but they see not one but thousands of candidate galaxies, each a potential home for the cosmic cannon. Which one holds the secret, without a simultaneous flash of light or a burst of neutrinos to narrow it down? The true source of this extragalactic champion remains just one more anonymous speck in a sea of infinity, a perfect letter from a sender whose name we cannot read. Even our most advanced methods can disagree on the basic facts. This cosmic ray delivered a clear and powerful signal, but when scientists rushed to calculate its energy, they were met with a frustrating split in the data. The ground array, a field of detectors that counts the number of secondary particles reaching the Earth's surface, provided one answer. It measured the particle density, the sheer number of particles per square meter, and from that calculated a certain energy value. Meanwhile, the fluorescence telescopes, which watched the faint ultraviolet glow of the shower developing in the air, told a slightly different story. They measured the total light yield, the amount of energy deposited in the atmosphere, and came up with a different number for the very same event. The discrepancy was not huge, but it was significant enough to place the particle's true energy in a zone of uncertainty, a gray area that could shift its classification from merely extraordinary to truly universe-breaking. This is not a failure of science, but a revealing look at its inner workings. The two methods are fundamentally different. The ground array is like trying to gauge the power of a rainstorm by counting how many raindrops hit a grid of buckets on the ground. The fluorescence technique is like estimating the storm's power by measuring the total flash of a lightning bolt that lit up the entire sky. Both are valid, but they measure different parts of the same complex phenomenon. For this particular cosmic ray, the two views of its death did not perfectly align, leaving its ultimate power shrouded in a veil of systematic uncertainty. This event forces us to confront a humbling reality. The mystery of these cosmic rays is not just out there in the voids of space, it is also right here in our own instruments and our interpretation of their data. Every number we quote, every energy we record, carries with it a hidden margin of error, a quiet acknowledgement that we are still refining the very tools we use to read the universe's most extreme messages. A cosmic ray once seemed to offer the perfect clue, its arrival direction pointing tantalizingly close to a brilliant, nearby active galaxy. This was Centaurus A, a well-mapped celestial powerhouse just over 10 million light-years away, with a monstrous black hole at its core spewing colossal jets of matter. For a moment, it felt like the mystery was finally over. Here was a known, violent object, a perfect suspect, and a cosmic ray that appeared to have its address written all over it. The hope was that this specific particle could act as a standard candle, a golden reference point. In astronomy, a standard candle is an object with a known, fixed brightness, allowing you to measure vast distances across the universe. For cosmic ray physicists, a standard candle would be a source whose properties are so well understood that detecting a ray from it would unlock everything. We could study how the particle traveled, how magnetic fields bent its path, and finally calibrate our entire understanding of these extreme events. This one candidate ray promised to be that key. But hope is a fragile thing in the face of data. Upon deeper investigation, the correlation began to fray. The timing was all wrong. While the ray's reconstructed path pointed near Centaurus A, it was impossible to prove it came from there. More critically, when astronomers checked the historical data, the galaxy was not in a particularly active state when the particle would have been launched. It was quiet, like a gun that had not been fired in centuries. There was no simultaneous flare in radio waves or X-rays, no burst of activity that could have been the obvious shot from the cosmic cannon. The connection was a coincidence, a chance alignment on the sky that ultimately led to another dead end. This near miss highlights a profound longing in the field, the search for a single, undeniable smoking gun. Just one event, one ultra-high-energy cosmic ray that we can definitively link to a specific astrophysical source at the exact moment of its emission, would crack this mystery wide open. It would transform the entire search from a statistical guessing game into a targeted investigation. We are all waiting for that one perfect messenger, the one that does not just point toward the darkness but finally turns on a light. A cosmic ray arrived at a moment that made the entire astrophysics community hold its breath. It was recorded around the same time that gravitational wave observatories felt a tremor in the fabric of space-time, a ripple caused by the violent collision of two neutron stars in a distant galaxy. For a fleeting moment, scientists dared to connect the two events. Could this specific ultra-high-energy particle have been a fragment of that cosmic cataclysm, a piece of stellar shrapnel from the most powerful explosion since the Big Bang? The theoretical possibility is profoundly compelling. A neutron-star merger is a forge of almost unimaginable violence. When two of these ultra-dense stellar corpses spiral into each other, they create a maelstrom of powerful magnetic fields and immense shock waves. Theorists suggest that in this chaotic environment, particles could be caught in these shock waves and accelerated again and again, like a speck of dust caught in a continuous series of detonations, until it reaches a velocity approaching the speed of light. This single cosmic ray became a symbol for this entire class of short-lived, catastrophic events. It represents the hope that the sources of these mysterious particles are not hidden monsters, but brilliant, transient fireworks that we are only just learning to see. The challenge, of course, is that space is vast and time is long. The chance that this specific ray was truly from that specific merger is infinitesimally small. It was almost certainly a cosmic coincidence, yet its timing makes it a perfect teaching tool, a thought experiment made real. It forces us to consider that the universe might be filled with these brief, brilliant accelerators that flare into existence for a moment, fire a handful of impossible particles into the void, and then vanish forever into black holes or clouds of heavy elements. This is the cutting edge of multi-messenger astronomy, the dream of using every type of signal at our disposal, gravitational waves, light, neutrinos, and cosmic rays, to triangulate the truth. We are building a network of observatories that listen for the groan of spacetime, watch for the flash of light, and wait for the impact of a single charged bullet, all hoping that one day, all these messengers will arrive from the same event, finally telling us the full story of the cosmic canon. Some cosmic rays seem to point an accusing finger at the very substance of reality. This 36th cosmic ray is a prime suspect in the case for exotic physics. A messenger whose arrival is so clean and whose origin is so perfectly blank that it fits a startling profile, the decay of a super-heavy dark matter particle. Imagine a single hypothetical particle left over from the Big Bang, a relic billions of times more massive than a proton, drifting unseen in the vast halo of our galaxy. This particle would be unstable, and after an eon of silence, it could spontaneously disintegrate, its immense mass energy converting directly into a burst of standard particles, including one single ultra-high-energy proton or nucleus that screams toward Earth. This is not a gradual acceleration process like a cosmic slingshot. It is a sudden, explosive birth, a particle appearing with its full energy already intact, as if materializing from the void itself. The beauty of this dark matter decay theory lies in its elegant explanation for a baffling observation, the isotropic distribution of these rays. They arrive from all directions equally, not clustered around galaxies, because dark matter is not concentrated in the bright galactic disks. It forms a vast spherical cloud enveloping our entire Milky Way and permeates the empty voids between galaxies. A cosmic ray born from dark matter decay could just as easily come from the dark, empty spaces between the stars as from the crowded city center of a galaxy cluster. This particular ray's energy and composition make it a favorite subject in theoretical papers exploring physics beyond the standard model. It is a tangible clue that these cosmic bullets are not just probing distant astronomical objects, but are potentially testing the fundamental ingredients of the cosmos itself. Every time one of these perfect, sourceless particles arrives, it whispers the same tantalizing question: are we seeing the final, explosive signature of the universe's most elusive and abundant form of matter? This next cosmic ray is a theorist's dream, a particle that seems to ignore the need for a cosmic accelerator entirely. Its staggering energy and its arrival from a perfectly random, empty patch of sky make it the perfect poster child for a radical class of explanations known as top-down models. Forget colossal black holes or colliding galaxies. Top-down theories propose that ultra-high-energy cosmic rays are not painstakingly accelerated by astrophysical objects. Instead, they are the decay products of something even more fundamental and ancient, born in the first moments of the universe. Imagine a cosmic fruit tree where the fruits are the cosmic rays we detect. Bottom-up models are like conventional farming, where you plant a seed, nurture it, and slowly grow the fruit to maturity through a long process. Top-down models are the opposite. The fruit simply falls, fully formed and ripe, from a branch that has existed since the dawn of time. These theories point to hypothetical, primordial particles or cosmic defects left over from the Big Bang. These relics would be unimaginably massive, billions of times heavier than a proton, and inherently unstable. After drifting through the cosmos for eons, one could spontaneously decay, its immense mass energy converting directly into a shower of standard particles, including a single, ultra-high-energy proton that rockets across space. The beauty of this idea is how neatly it explains the most baffling observations. Why do so many of these rays point back to empty voids? Because these primordial particles are not tied to galaxies. They are woven into the entire fabric of space-time, equally present in the crowded galactic clusters and the vast, dark deserts between them. Why do they have energies that defy the UHECR cutoff? Because they are not travelers on a long journey. They are born with that energy right in our cosmic neighborhood, appearing as if from nowhere. While top-down models remain highly speculative and are not the mainstream view, they stubbornly persist as a viable alternative for one simple reason. The bottom-up models, which rely on known astrophysics to accelerate particles, face their own severe and seemingly insurmountable challenges. No known object can easily account for the raw power, the mixed composition, and the random arrival directions we observe. So when a cosmic ray like this one arrives clean and sourceless, it forces us to ask a profound question. Are we missing a hidden class of cosmic engines, or are we witnessing the final, fading whispers of the universe's violent birth? This specific cosmic ray is a single thread in a much larger tapestry. While we cannot trace its individual path back to its source, its slight deflection is a vital clue. Every ultra-high-energy cosmic ray that passes through the Milky Way is gently nudged and twisted by our galaxy's invisible magnetic field. Imagine these particles as countless tiny compass needles, each one subtly tugged by the magnetic currents they pass through on their way to our detectors. Their final arrival direction is not a true map of their origin, but a scrambled image distorted by the magnetic lens of our own galaxy. But here is the brilliant twist. When scientists gather a large collection of these events, a pattern begins to emerge from the chaos. By studying the statistical distribution of their arrival directions, by seeing how entire populations of rays appear to be shifted in one part of the sky compared to another, astronomers can work backward. They can use the cosmic rays themselves to indirectly map the structure of the galactic magnetic field. This particular ray, number 38, is one more data point in that grand reconstruction. Its deflection, combined with thousands of others, helps scientists learn about the field's strength and its intricate orientation, tracing the vast, invisible magnetic arches and currents that weave between the stars. So this cosmic ray is not just a mystery to be solved, it is also a precise tool. It helps us understand the fundamental architecture of our own cosmic backyard, the very magnetic pathways that guide and scramble these incredible messengers. We are using the universe's most elusive particles to finally see the invisible forces that shape our galactic home. Our cosmic mystery suddenly shifts from a question of power to one of identity. The 39th cosmic ray arrived with an energy that placed it right at a contentious crossroads, a specific point in the spectrum where the fundamental nature of these particles seems to transform. For years, data has hinted at a strange and confusing pattern, a composition switch. At the very highest energies, the air showers suggest the primary particles are often heavy nuclei like iron. But at slightly lower, yet still astronomical energies, the evidence seems to flip, pointing toward lightweight protons. This single event landed squarely in the transition zone, its own atmospheric fingerprint providing a crucial vote in this high-stakes debate. The particle's identity is not a trivial detail, it is the single most important clue to its origin. Different cosmic accelerators leave different fingerprints on their ammunition. Imagine two different types of factories, one designed to forge solid iron cannonballs and another that produces finely crafted lead shot. If you find a cannonball at the scene, you know which factory to investigate. In cosmic terms, a heavy iron nucleus is a fragile, complex object. It cannot survive a long, tortuous journey across millions of light years. Its detection strongly implies a relatively nearby source, a galactic forge not too far from home. A single proton, however, is a rugged, simple traveler. It can theoretically come from anywhere in the universe, its path hopelessly scrambled by magnetic fields along the way. The existence of a composition switch completely upends any simple theory. It suggests we are not dealing with one type of cosmic engine, but with many. Perhaps the most violent local accelerators specialize in forging heavy bullets, while more distant, gentler sources produce a stream of lightweight protons that only seem to dominate when the heavy ones cannot reach us. This 39th ray, with its ambiguous signal, refuses to pick a side. Its shower profile was not clearly that of a proton or an iron nucleus, but something frustratingly in between. It adds weight to the terrifying possibility that the mix of particles arriving at Earth is constantly changing, a chaotic soup of different projectiles from a whole zoo of hidden cosmic beasts. With each new event like this, the simple hope of finding a single answer fades, replaced by the daunting realization that the universe's particle accelerators are as diverse and mysterious as the particles they create. Not every cosmic anomaly arrives with a thunderous declaration. The 40th cosmic ray was a quiet infiltrator, its signal almost lost in the constant drizzle of lower energy particles that perpetually bathe our planet. It was only through meticulous energy reconstruction, a painstaking forensic analysis of its faint atmospheric footprint, that scientists could confirm its true identity. This was no ordinary cosmic ray. It belonged to the elite class of ultra-high-energy events, a wolf hiding in a vast flock of sheep. This background event forces a humbling perspective. The journey to understand the universe's most powerful projectiles is not a clean hunt for a few spectacular outliers. It is the challenge of finding a handful of impossibly rare needles in a cosmic haystack of unimaginable size. The air around us is constantly buzzing with countless cosmic rays from the Sun, from distant supernova within our galaxy, and from the faint, ancient glow of the Big Bang itself. Spotting a true ultra-high-energy event requires sifting through this immense background noise, separating the local chatter from the deep, distant scream of a cosmic cannon. This continuous spectrum reveals a deeper truth. There is no sharp, magical energy wall that separates the possible from the impossible. The mystery of the 50 ultra-high-energy cosmic rays is not an isolated puzzle. It is simply the most extreme, most baffling expression of a question that has persisted for over a century. Where do any cosmic rays come from? We understand the lower energy ones a little better, tracing some back to stellar explosions in our galactic neighborhood. But as the energy climbs, the sources become more obscure, the physics more extreme, and the answers more elusive. The 50 cosmic mysteries we are exploring are not separate from this grand continuum. They are the final, terrifying cliff edge of a vast and unknown landscape, a reminder that the greatest enigmas of the cosmos often lie at the boundaries of our perception, hidden in plain sight among the ordinary. A cosmic ray struck the atmosphere with such perfection that its digital echo became a work of art. This is cosmic ray number 41, a particle immortalized not just in scientific papers, but in vibrant, swirling animations that light up screens in classrooms and museum exhibits worldwide. When this event was processed, the data painted a stunningly clear picture, a beautiful and symmetrical cascade of secondary particles fanning out across the detector array in a near-perfect circle. In public presentations, this single event is a showstopper. It is the public outreach star, transforming abstract terabytes of data into an intuitive visual story. You do not need to understand electron volts to see the elegant, destructive power unfolding in that animation. You can simply watch the simulation and feel the awe of something immense and mysterious arriving from the void. This communication is not a trivial side project. It is a vital lifeline for this entire field of science. Building observatories that span hundreds of square miles requires immense public investment and societal goodwill. The quest to understand particles from deep space does not offer an immediate practical application. It is a fundamental human pursuit, a search for answers to the most basic questions about our universe. An event like this, with its undeniable visual punch, bridges that gap. It translates complex, elusive science into a shared experience of wonder. That moment of shared awe is more powerful than any list of facts. It captures the imagination of a student who might one day design the next generation of detectors. It helps a taxpayer understand why we gaze into the emptiness, searching for meaning. The mystery of this particular cosmic ray remains entirely unsolved. We still have no idea where it came from, but its greatest legacy may not be the data it provided to physicists, but the inspiration it provides to everyone else. It proves that the pursuit of knowledge, even when it leads to deeper questions, is a story worth telling, a beautiful and necessary human endeavor. A single data point can sometimes carry the weight of a universe. This 40-second cosmic ray did not just arrive with immense power, it arrived with a specific set of properties that acted like a key, locking one theoretical door forever. For years, a popular and elegant model had captivated theorists. It suggested that the most powerful cosmic rays were born within colossal shock waves, rippling through the vast, empty spaces between galaxy clusters. These intergalactic tsunamis, generated by the slow-motion collisions of the universe's largest structures, were thought to be perfect natural accelerators, capable of surfing particles to unbelievable speeds over millions of light years. The theory was beautiful. It leveraged known physics and the grand architecture of the cosmic web. Then this particular cosmic ray was measured with exquisite precision. Its energy was off the charts, but more importantly, its composition was clearly that of a lightweight proton, and that was the detail that broke the model. According to the shock wave theory, a proton accelerated in those vast, diffuse regions would have a very long path to reach its top speed. But the mathematics showed a hard limit, a maximum energy that such a process could ever impart to a single proton. The energy measured for this event was a clean, undeniable 20% above that calculated ceiling. It was not a matter of tweaking the numbers. The particle had simply arrived with more punch than the entire theoretical engine was capable of delivering. It was like finding a single arrow that had flown farther than the strongest bow on Earth could possibly shoot. The implications were immediate and brutal for the theory. This was not a statistical fluke or a measurement to be debated. It was a direct falsification. The shock wave model, for all its elegance, could not be the primary source of these ultra-high-energy protons. A single, well-measured event had pruned a major branch from the tree of possible explanations. This is how science often truly advances, not by slow confirmation, but by sudden, decisive contradiction. That one cosmic bullet forced theorists back to their chalkboards, erasing whole pages of calculations and opening their minds to wilder, more violent, and more exotic possibilities hidden in the dark. The 43rd cosmic ray forces a moment of scientific humility, demanding we acknowledge the simplest explanation of all. With such a tiny number of these monumental events, some of the bizarre properties we assign to them could be nothing more than statistical noise, a random roll of the cosmic dice. This particular particle arrived with a strange atmospheric fingerprint, a shower profile that did not neatly match the expected pattern for a proton or an ion nucleus. It was an outlier, an anomaly that could hint at new physics or an exotic particle type. But before we rewrite the laws of the universe, we must confront the mundane reality of chance. Think of it like flipping a coin 100 times. You expect roughly 50 heads and 50 tails, but it is entirely possible, just by random luck, to get a run of 10 heads in a row. That run is not evidence of a weighted coin, it is a simple statistical fluctuation. In the same way, this cosmic ray could be that run of 10 heads, a perfectly normal particle that, through the random chaos of its collision with our atmosphere, produced a shower that looks unusual to our detectors. Its strange direction, pointing to an empty void, might also be a fluke. With only a few dozen of these events on record, a small cluster pointing to nowhere is statistically likely to occur purely by accident. This is the constant, humbling challenge of frontier science. We are searching for a faint signal in an ocean of randomness, and our own desperation for a pattern can sometimes trick us into seeing one where none exists. Every unusual event must survive the ruthless test of probability. Is it a true message from a new kind of cosmic phenomenon, or is it just the universe's background static mimicking a signal? This is why scientists relentlessly pursue larger datasets. Building bigger observatories is not just about catching more rays, it is about drowning out the noise. With 10 times the number of events, a strange fluctuation like this one would either be joined by other, similar anomalies confirming a true pattern, or it would be revealed as a solitary oddity, swallowed by the overwhelming weight of normal data. This cosmic ray, therefore, is a cautionary tale written in the sky. It reminds us that the path to discovery is paved with patience and a healthy skepticism, forcing us to ask with every new detection, is this the whisper of a secret or just the random sigh of an indifferent universe? This specific cosmic ray is a ghost from the future, a preview of the answers we do not yet have. Its faint signal is a placeholder, a single frame from a movie we are only just beginning to film. The next generation of cosmic observatories is being designed right now, built to catch particles just like this one and finally read their hidden stories. The proposed Auger Prime upgrade will transform the existing Pierre Auger Observatory into a more discerning instrument. Its new plastic scintillator detectors will sit atop the classic water tanks, allowing scientists to better distinguish between the showers created by protons and those from heavier nuclei. For a cosmic ray like this 44th mystery, that distinction is everything. Knowing its true composition with certainty would tell us if it was a hardy long-distance traveler or a fragile local product, instantly narrowing the search for its source. Meanwhile, projects like the Giant Radio Array for Neutrino Detection, or GRAND, plan to use a completely different technique. Imagine hundreds of thousands of simple radio antennas scattered across mountainsides, listening not for light or particles, but for the faint radio waves generated when an ultra-high-energy cosmic ray slams into the atmosphere. This method could allow GRAND to cover a colossal area, 100,000 square kilometers, catching these rare events in vastly greater numbers. Higher statistics are the ultimate weapon against uncertainty. With 1,000 of these events instead of a few dozen, the faint patterns we see today, the potential clusters and anisotropies, would either solidify into a clear map or vanish into the noise. We would know definitively if we are surrounded by a uniform drizzle or targeted by specific cosmic cannons. These future instruments will also peer deeper into the lower energy regime, searching for the missing links between the common galactic rays and the extraordinary extragalactic ones. They will catch the particles that are just shy of the impossible, building a complete family tree of cosmic acceleration. This cosmic ray, number 44, represents the hope that the current era of confusion is merely a prelude. It is a promise that the universe is not trying to hide its secrets forever, only until we build the right tools to listen. Every unsolved mystery today is a blueprint for the discovery of tomorrow. A cosmic ray can be a compass for the void itself. This 45th messenger did more than just carry an impossible amount of energy. It acted as a subtle probe for the most elusive of forces, the magnetic fields that stretch between galaxies. We often picture the space between these colossal star cities as a perfect, empty vacuum, but it is not. It is threaded with faint, invisible lines of magnetic force, a ghostly web whose strength and structure remain one of the great unknowns in cosmology. When an ultra-high-energy cosmic ray like this one, a charged particle such as a proton, travels across hundreds of millions of light-years, it does not fly straight. It is constantly nudged and curved by these extragalactic fields, its path becoming a winding, corkscrewing route through the cosmic darkness. We cannot see these fields directly, and we cannot measure them with any conventional telescope. But we can read the bends they impart on these high-speed projectiles. For a specific event where we have a good estimate of the particle's composition and its immense energy, its final arrival direction gives us a tiny, precious clue. If the particle's path seems only slightly scrambled, it suggests the magnetic fields in the voids it crossed are weak and disorganized, like a gentle, chaotic breeze. If, however, its trajectory is wildly different from where we think it started, it points to stronger, more coherent fields out there in the emptiness, perhaps vast rivers of magnetic force flowing through the cosmic web. This single cosmic ray provides one data point, one tiny constraint on the invisible architecture of intergalactic space. It transforms the particle from a mere message into a scientific instrument, a natural probe that has sampled the magnetic conditions across an unimaginable gulf of nothingness. Every such event is like sending a single, blind sensor on a million-year journey through the dark and waiting for its final report. The story it tells is not just about where it came from, but about the very fabric of the universe it passed through to get here. The 46th cosmic ray is a confrontation with our own ignorance. This particular event is so clean and yet so baffling that it forces us to admit a terrifying possibility. We may not even know the right questions to ask. Every other mystery we have explored, from the UHECR cutoff to magnetic scrambling, operates within the known framework of physics. We are trying to fit these cosmic square pegs into the round holes of our established theories. But what if the pegs are not square at all? What if they are shapes we have not yet learned to name? This ray represents the ultimate unknown unknown, a category of mystery so profound we cannot yet define its edges. It whispers that the true explanation for these particles might not be a hidden galaxy or a new particle decay, but an entirely new branch of astrophysics or a fundamental physical process we have not yet conceived. Perhaps the universe has a method for accelerating matter that defies our entire understanding of energy and force, a cosmic principle operating in the dark, voids that our textbooks have not yet imagined. This is the pure, unadulterated mystery, the kind that does not yield to bigger detectors or more complex calculations alone. It awaits a revolutionary insight, a future genius who will look at the same data and see a pattern invisible to us, who will ask a question no one has thought to pose. The ultimate answer may not be a what, but a how, a new law of nature written in the language of these impossible bullets, waiting for the one who can finally read it. Raw data from a cosmic impact does not arrive as a neat, pre-packaged fact. It is a chaotic digital scream, a storm of electronic pulses that must be tamed and interpreted. The 47th cosmic ray delivered exactly this kind of puzzle, its signal so unusual it nearly slipped past the automated filters designed to find it. When it struck, it did not produce the clean, sharp pulse that analysis software is trained to recognize. Instead, it left a distorted, lopsided signature in the detectors, a waveform that looked more like a glitch than a genuine event from the depths of space. The automated system, programmed to discard noise, initially flagged it for deletion. It was a ghost in the machine, an anomaly within an anomaly. Only the keen eye of a human analyst reviewing the logs of rejected data noticed the pattern. The strange pulse shape was not random static. It was the precise fingerprint of an ultra-high-energy particle hitting the very edge of the detector array at an extreme angle. Its cascade of secondary particles creating an asymmetric echo that the standard algorithms had never been taught to see. This single event forced a collaboration between physicist and programmer, a fusion of scientific intuition and computational skill. They had to teach the machine to see what it had been blind to, refining the software with new, more complex pattern recognition algorithms. This is the hidden engine of cosmic discovery, the unglamorous work of data scientists and software engineers who write the code that translates raw electronic noise into a cosmic address. Without their ingenuity, the universe's most subtle whispers would be lost forever in a sea of digital static. A reminder that the quest to understand the cosmos is fought not only with giant telescopes, but with lines of code and the relentless pursuit of a clearer signal amidst the noise. A single event notification flashed across monitors in research institutes from Argentina to Poland, from Japan to the United States. Cosmic ray number 48 was not just a particle, it was a global event, its data instantly shared across a network of scientists spanning dozens of countries. This is the daily reality at the Pierre Auger Observatory and other great collaborations, a testament to the fact that no single nation can solve this cosmic puzzle alone. The scale of the mystery demands a scale of effort to match. Imagine the resources required to build and maintain an observatory that covers 3,000 square kilometers of the Argentine pampas. No single university, no single government could hope to fund or staff such a monumental undertaking. It requires a worldwide alliance, a pooling of intellect, money, and sheer human determination. The analysis of this one particle's journey reflects that diversity. A theorist in Italy might be modeling the magnetic fields it passed through, while an engineer in Germany checks the calibration of the water tanks that recorded its signal. A data scientist in Mexico might be refining the algorithms that reconstructed its energy, while a doctoral student in the United States scans telescopic surveys of its arrival direction. Each brings a unique piece of the puzzle, a different perspective shaped by their own culture and training, yet all united by the same fundamental question. This international effort is humanity's greatest strength in the face of the cosmos's grandest secrets. The detectors themselves are a monument to this cooperation, bearing the names and flags of the many nations that helped build them. When cosmic ray 48 struck, it was not an American particle or a European particle. It was a human discovery. Its brief, brilliant passage through our atmosphere became a shared piece of data, a common problem for the entire world to ponder. In an age often defined by division, the silent, patient work of these global collaborations offers a powerful counter-narrative. It proves that our curiosity about the universe can transcend borders, that the desire to understand our place in the cosmos is a universal human trait. The mystery of the ultra-high energy cosmic rays will not be cracked by a lone genius in an isolated lab. It will be solved by a chorus of voices, speaking in different languages but asking the same question, working together to read the message carried by a single, impossible speck from the void. This 49th cosmic ray does not just defy physics, it challenges our very perception of reality. Its existence is a quiet, persistent statement from the cosmos, a demonstration that nature operates on a scale of power and violence we can scarcely imagine, much less replicate. All our grandest human achievements, our most powerful particle colliders, and our most brilliant engineering are like children's toys next to the effortless cosmic forces that launched this single particle across the void. What does it mean that the universe casually produces energies millions of times beyond our own capabilities, not in a rare, singular explosion, but as a recurring, almost routine phenomenon? This particle is a lesson in cosmic humility, a reminder that we are not the center of a benevolent, orderly system, but temporary residents in a realm of immense and indifferent power. The randomness of its arrival, a bullet fired from an unseen gun in the dark, speaks to a universe that is not finely tuned for our existence, but one where we are a fragile, fortunate accident. We are living on a world constantly bombarded by forces that could, in an instant, erase all life, yet they pass through us unnoticed, their violence spent on the thin shield of our atmosphere. This cosmic ray forces a profound shift in perspective. It moves the question from a scientific puzzle to a philosophical one. Are we insignificant specks in a chaotic and meaningless cosmos, or is our ability to detect this particle, to ask these questions and feel this awe, itself a kind of miracle? The true message of this messenger may not be about its origin, but about our own place in the grand and terrifying scheme of things, a tiny spark of consciousness gazing into the abyss, humbled by the sheer, effortless might of the darkness. The 50th cosmic ray arrived as a perfect echo of all the others, a final unsolved case file in a drawer filled with 50 identical mysteries. Its energy was immense, its trajectory precise, and its origin, like the 49 that came before it, was a perfect blank. After decades of research, with the world's most brilliant minds focused on the problem and observatories spanning continents, a definitive explanation for these ultra-high-energy cosmic rays remains completely beyond our grasp. We have mapped their impacts with stunning clarity, yet the shooters remain hidden in the dark. This final messenger is not an ending, but a symbol of the quest itself. It represents a fundamental truth about our relationship with the cosmos, that the universe is under no obligation to make sense to us on our timeline. We build ever larger machines to listen, and the void answers with the same silent, impossible bullet, a reminder that some secrets are guarded not by distance, but by the very limits of our imagination. The case remains open, the investigation continues, and the greatest discovery is still waiting in the dark, carried on the next particle from the void. These 50 cosmic messengers, each a singular enigma, weave together into a tapestry of shared mysteries. 4 great puzzles bind them all. First is the profound silence of their origins, the consistent pointing toward empty voids that defies every map of known cosmic power. Second is the maddening confusion over what they even are, a chaotic mix of lightweight protons and heavy ion nuclei that suggests not one, but many different types of hidden accelerators. Third is their blatant defiance of a fundamental law of physics, the UHECR cutoff, arriving with energies that should have been drained away eons ago by the cold fog of deep space. And finally, there is the cosmic scrambling, the invisible hand of magnetic fields that twists their paths, erasing their return addresses and leaving us with a hopelessly tangled celestial map. Individually, each of these problems is a formidable challenge. Together, they form an impenetrable wall. This is not a puzzle that will be solved by simply building a bigger detector or by tweaking an existing equation. The collective testimony of these 50 events points to something far more profound, a fundamental gap in our understanding of how the universe operates at its most violent extremes. Cracking this code will demand more than just incremental progress. It will require a true paradigm shift, a completely new way of seeing the cosmos and the unimaginable forces that shape it. 50 cosmic bullets have struck and 50 mysteries remain. They are not errors in our data or flaws in our instruments, but real and persistent messages from the most violent corners of existence. Each one is a courier from a realm of physics we have not yet learned to name, carrying secrets about forces that dwarf anything we can create. Their origins are silent, their compositions a chaotic mix, and their very existence defies the fundamental laws we thought governed cosmic travel. The universe is not just stranger than we imagine, it is stranger than we can imagine, and these particles are the proof. So the next time you find yourself under a clear night sky, look up. Remember that in that vast, silent darkness, invisible projectiles of impossible power are slicing through the void, each one a perfect riddle without an answer. Your world is constantly being touched by these cosmic enigmas, a silent rain of wonders that invites us to keep searching, to keep questioning, and to embrace the beautiful, humbling truth that the greatest adventures lie in the mysteries we have yet to solve.